Alright, so today we're going to be talking about something called improper integrals. And in a nutshell, these are integrals where we need to rely on our knowledge of limits to be able to evaluate the integral. And so I think the best way to motivate this is through an example. So I'm just going to start off with an example. Let's say we have the equation y is equal to minus x over 2. And we want to find the area of this. We want to find the area of this curve in the first quadrant. Or like find the area of this curve bounded on the first quadrant. And one thing we'll notice is that this equation will never actually intersect the x-axis because it has a horizontal asymptote at the x-axis. So because this is an exponential decay kind of function, it will look something like this, where we'll get closer and closer to the x-axis, but we'll never actually hit the x-axis. So you might expect that because of the fact that we will never have an intersection at the x-axis, our area might be infinite. But in some cases, the area actually converges, right? We have seen so many examples of where we have some convergent behavior when we tend towards infinity. And so that's sort of the motivation of improper integrals, where we want to evaluate things where we require our knowledge of limits to be able to evaluate our integral. So we want to find this green area. And so this is dx and this is the height. And so the integral that will help us evaluate the area is simply the integral from 1 or 0 to some constant b, and it is of e to the minus x over 2 dx. And if I were to just evaluate this integral, that would give me that's equal to minus 2e to the minus x over 2 from 0 to b. And because we want to evaluate this integral all the way as b tends towards infinity, we'll be using limits. So we'll be having something like limit as b tends to infinity of this term. And when we simplify that, we'll get something like negative 2b times, or to the power of x over 2, or sorry, what am I doing? Negative 2e to the power of negative b over 2 plus 2 times e to the power of 0, and the limit of that as b tends towards infinity. This just the right side just evaluates to 2, and then as b tends towards infinity, we know that this term e to the negative infinity will go towards closer and closer to 0. So we're just gonna, this whole term over here will just tend towards 0. And so our total area evaluates to 2. So notice how even though we did not have an x and we're taking the upper limit towards infinity, our area does converge. And we could only find this convergent behavior through our machinery of the limits. And that's what improper integrals are. Improper integrals are basically any integrals where we would need some sort of limit machinery to be able to solve the integral. So the first class of improper integrals are the following. These are improper integrals with infinite integration limits. And we saw an example of that earlier. But let's formalize everything. So basically, anytime where we want to take, when our limits are going to go tend towards infinity or negative infinity, we'll have a type of improper integral. So the first class is when f of x is continuous on a towards infinity, and this is a bracket where this is a parentheses. Then the integral from a towards infinity of f of x dx is simply equal to the limit as b tends towards infinity of a to b. So I've replaced infinite upper bound with b, because I can use to be able to express it with a limit of f of x dx. Now, if our domain is now negative infinity to b, where we want to find the integral of, then we would have our integral look something like negative infinity to b of f of x dx. And that's the same thing as limit as a tends towards negative infinity of a to b of f of x dx. And finally, if we have a limit that we want to find on both sides going towards infinity, then this integral, which we will want to evaluate, of f of x dx, is simply equal to the limit as a tends towards negative infinity of a to some constant c. And you can choose the c to be whatever value makes the evaluation of our integral easy, plus c to, or sorry, I forgot to add the limit, plus the limit as b tends towards infinity of c to b f of x dx. So I've simply added the c as a constant, so I can write it as two different limits. And then to evaluate these two limits is just one of these examples over here. And so that's how you'd deal with improper integrals, where we want to have our upper and lower limits tend towards a side of infinity. But one thing to note is that in the example that motivated all of this, we saw that we converged to a value, right? So that's not always necessarily the case. The limit might not actually converge. So what I mean by that is if the limit, so if these evaluations is finite, so we get a constant value back, then the improper integral converges. But if a finite limit fails to exist, then our integral diverges. So we're not always guaranteed to have a kind of a finite limit that we would evaluate to when we use these improper integrals. And when that's not the case, then we can say that the limit diverges. And I mean, an easy example of that is, like, for example, if we were to take the if we were to integrate x squared from 0 to like infinity, clearly, like, we're not going to have something finite that this limit evaluates to, because x squared will continue to get larger and larger, and so we're not really going to have some value that we converge towards, right? So our improper integrals are not necessarily convergent. All right, so let's work with evaluating different improper integrals, and hopefully that will strengthen this concept. So let's try to evaluate the integral from 1 to infinity of dx over x. And so this is the same thing as the limit as b tends towards infinity of the integral from 1 to b dx over x. We can rewrite this as ln x from 1 to infinity of, or sorry, not 1 to infinity, from 1 to b, and limit as b tends to infinity. And that's just saying the limit as b tends to infinity of ln b minus 0. And clearly, as b tends towards infinity, the natural log of b will also tend towards infinity. And so we get infinity, and therefore the integral diverges. So here is an example of a non-convergent integral. Let's do a second example. Evaluate the integral from negative infinity to infinity of dx divided by 1 plus x squared. Now, this is the same thing as us trying to split this integral into two separate integrals and evaluating each of those. What I mean by that is we're going to split this into the integral from negative infinity to, let's just use 0, because this was the integral of this is tan inverse, so tan inverse of 0 is just 0. So yeah, the integral of that plus the integral of 0 to infinity of dx divided by 1 plus x squared. That's the same thing as the limit as a tends towards negative infinity of a to 0 of dx plus 1 plus x squared plus limit as b tends towards infinity of 0 to b of dx over 1 plus x squared. That will be equal to the limit as a tends towards negative infinity of tan inverse of a minus 0 plus limit as a tends towards infinity of, or actually, sorry, this is minus tan inverse of a plus 0. I flipped the order because a is the, or 0 is the upper limit, so 0 and then minus tan inverse of a. And then limit as b tends towards infinity of tan inverse of b minus 0. As b tends towards infinity, tan inverse of infinity is simply pi over 2. And so that's the evaluation of this side. And then the tan inverse of negative infinity is negative pi over 2. And then we have that negative sign in front. So that will evaluate to pi over 2. And so pi over 2 plus pi over 2 is simply pi. All right. So that was another example of an improper integral. And let's try to determine the integral of 1 to infinity of dx over x over p. So over here, p is p represents the degree of this power function, and what we want to try to determine through this is for what values of p does this integral converge, and for what values of p does this integral diverge. For now, it might not seem very important why we're doing this specific problem, but when you get into like series and testing for convergence, this benchmark is very important. So this integral is the same thing as the limit as b tends towards infinity of 1 to b of dx over x to the power of p, and that evaluates to the limit as x or b tends towards infinity of 1 over minus p plus 1 times x to the power of minus p plus 1. And then that from 1 towards b. And that's just the same thing as the limit as b tends towards infinity of 1 over 1 minus p times b to the power of 1 minus p minus, if we plug in 1 over here, 1 to the power of anything is just 1. And so what we're left with is just minus 1 over 1 minus p. So we can take 1 minus p common, and so that's the same thing as limit as b tends towards infinity of 1 over 1 minus p times b to the power of 1 minus p minus 1. And so we're taking b towards infinity, right? And clearly, like, if you can notice something over here, if p, well, okay, we already know that when p is equal to 1, all this integral is, these integrals are not valid, because then the integral would be a log function. So when p is equal to 1, we diverge. And so all of this analysis is for p greater than or p not equal to 1. So that's where we're trying to analyze that's where we're trying to analyze this behavior of the limit. So we have this limit of b to the power of 1 minus p. And so if p is greater than 1, then b to the power of whatever we have, it's b to the power of some negative number. So the larger p becomes, the smaller this b to the power of 1 minus p is. So if p is greater than 1, because 1 minus p is less than 0, this whole term over here will tend towards 0 as b tends towards infinity. And therefore, we eventually just end up converging. So this, if p is greater than 1, then this limit will just evaluate to 1 over 1 minus p times negative 1, which is equal to 1 over p minus 1. Now, conversely, if p is less than 1, then this will be a 1 minus p will be positive. And so now our limit will go towards infinity because we're taking a large number and we're taking it to a positive power. So p is less than 1, then we get infinity. So that means the limit converges if p is greater than 1, and the limit diverges if p is less than 1. So the integral of dx over x to the power of p from 1 to infinity converges when p is greater than 1 and diverges when p is less than or equal to 1, because we have shown over here that when it's less than 1 it diverges, and then previously we have shown that when it's equal to 1 it also diverges. Alright, so that was an interesting proof. Let's move on to our second class of improper integrals. And so these are improper integrals with discontinuities. Alright, so what do I mean by improper integrals with discontinuity? So to motivate this, let's consider the equation y is equal to 1 over square root of x, and we again want to find the area of the infinite region in the first quadrant of this function. We know that this function is not defined at x is equal to 0. This is undefined, right? Because we're dividing by 0. But the question is it still possible to find the area of this function, even though we are never going to hit 0, but we will tend closer and closer to 0, and the function will kind of behave like this. And so let's say we want to find the area between x is equal to 1 and the y-axis. But because the function never touches the y-axis, we'll have an improper integral because we'll probably have to use limits to evaluate whether or not this function actually converges or not. So we want to find that green shaded region, and that's the same thing as evaluating an integral from 0 to 1 of 1 over the square root of x dx. But 1 over square root of x is not, the original function is not actually defined at 0. So we'll have to use limits, and we would have to rewrite this as the limit as a tends to 0 from the positive side of a to 1 of 1 over square root of x dx. So let's evaluate this. So that's just the same thing as the limit as a tends to 0 from the positive side of this is x to the negative 1/2, so we get 2 root x from a to 1, and that's the same thing as limit as a tends towards 0 from the positive side of 2 minus 2 root a. Now, as a tends towards 0 from the positive side, the square root of a will also tend towards 0, and therefore this limit just evaluates to 2. And again, we saw that even though the function never actually touches this y-axis, and we're going to be infinitely heading closer and closer to the y-axis, but we'll never hit the y-axis, we still get evaluated to a finite area. And the only way we were able to find the actual area was through our usages of improper integrals. So now that we have seen that motivating example, let's formalize improper integrals with infinite discontinuities. So improper integrals with infinite discontinuities. All right. So the first case is if our domain is from A to B, where we're not defined at A. So that's similar to the motivating example. So we're trying to evaluate the integral from A to B of f of x dx. And that turns out to be the same thing as the limit as you tend towards as the limit as x tend towards A from the positive side of f of x dx, and then the integral from a to b. The second case is where we are actually defined at the left side, but we're not defined at the right upper limit of b, and we're trying to evaluate the same integral from a to b of f of x dx, and that turns out to be the same thing as the limit as x tends towards as x tends to, also, this shouldn't be x over here. This should be as, let's just rename this to some constant c. And this is that c tends towards a from the positive side. And so this is also c tends towards, yeah, let me just rewrite this. The limit as c tends towards b from the left-hand side of the integral from a to c of f of x dx. The last one is if we are defined on the interval from A to C, where C is non-inclusive, and then from C to B, where B is inclusive and C is still not inclusive. So we still want to find out the integral from A to B, but we have a discontinuity in the middle of our domain. So when we want to find that integral, it's the same as finding the integral from A to C of f of x dx plus c to a of f of x, or c to b of f of x dx. And notice that when we are trying to, now we split this original problem into two subintegrals, and the left subintegral is basically a special case of this second case I described here because c is not defined in the domain, and the right subintegral is just a special case of this first one over here. So when we are trying to find out the integral where we're not defined in the middle of our domain, then we split it up at the undefined discontinuity, and then we can use the subcase 1 and subcase 2 to solve for the actual integral. So let's work with some examples of infinite discontinuities. So let's say we want to evaluate the integral from 0 to 3 of dx divided by x minus 1 to the power of 2 or 3. We know that at x equals 1, this function is not defined. So we have a discontinuity at 1. So we will want to evaluate the integral from 0 to 1 of dx over x minus 1 to the power of 2 or 3 plus the integral from 1 to 3 of dx divided by x minus 1 to the power of 2 or 3. Now, this integral is the same thing as, well, if we take this left integral to integrate first, then that's the same thing as the limit as b tends towards 1 from the left side of the integral from 0 to b d of x divided by x minus 1 to the 2 or 3, which is equal to us finding out, which is equal to Well, so this is going to be x minus 1 to the negative 2/3. Add 1 to that. That is going to be 1/3. And so that is just the same thing as 3 times x minus 1 to the 1/3. The limit as b tends to 1 from the negative side. And we want to evaluate that from 0 to b. That's the same thing as the limit as b tends to 1 from the negative side of 3 times b minus 1 to the 1/3 minus 3 times negative 1 to the 1/3. Therefore, simplifying all of this, we get limit as b tends to 1 from the left side of 3 times b minus 1 to the 1/3. And then negative 1 to the 1/3 is simply negative 1. And negative 1 times negative 3 is 3, so we get a plus 3 here. And now all that is left is for us to see what happens. Well, when we go to 1 from the left side over here, this will tend towards 0 as well. So 0 to the 1/3 is simply 0, and 0 times 3 is 0. So that evaluates to 3. And now we're done with that. Let's finish working with the second integral. So that is equal to the limit as b tends towards 1 from the positive end of b integral from b to 3 of d of x times x minus 1 to the 2/3. We know that's the same thing as the limit as b tends to 1 from the positive side of 3 times x minus 1 to the 1/3 from b to 3. That becomes limit as b tends to 1 from the positive side of 3 times 2 to the 1/3 minus 3 times b minus 1 to the 1/3. B minus 1 as b tends to 1 is 0, so this again evaluates to 0, and we're just left with 3 times the cube root of 2. And so adding our two evaluations up, our final answer is just 3 plus 3 times the cube root of 2. So that was evaluating an improper integral with an infinite discontinuity in the middle. Let's just do one more example. Let's evaluate the integral from 1 to 4 of dx over x minus 2. And so we have a discontinuity at x equals 2, since we will be dividing by 0, and hence this is the same thing as us wanting to do integral from 1 to 2 of dx divided by x minus 2 plus from 2 to 4 of dx over x minus 2. Let's start off with the left integral. So limit as b tends to 2 from the positive end of the integral from 1 to b of dx over x minus 2 is equal to the limit as b tends to 2 from the positive end of the natural log of x minus 2 x minus 2, or also this is not positive, this should be negative over here, of x minus 2 from 1 to b. That's the same thing as the limit as b tends towards 2 from the negative end of natural log of b minus 2, an absolute value, of course, minus the natural log of the absolute value of negative 1, which is just going to be 1, and log of 1 is 0. So as we go towards closer and closer to 2, this will be closer and closer towards 0, and the log of 0 as we go closer and closer to it will evaluate to negative infinity. So this is equal to negative infinity. And because one side of this integral is already diverged and goes towards negative infinity, doesn't matter what the right side evaluates to, because even if it will converge, because the left integral converged, whenever we try to add infinity or negative infinity, just some like converging thing, we're still gonna end up with a non-converging sum. So we can ignore the right side and just conclude that this is diverges. All right. Now let's do one final example. This is probably the hardest one. So let's find the volume of solid obtained when we rotate the curve y is equal to x times e to the x on the interval 0 is less than or equal to x is less than or equal to this about the x-axis. So if we were to draw a rough sketch of what this graph looks like on the first quadrant, because we're varied between 0 and infinity, initially we'll be increasing because x times e to the x, but later on we'll just tend towards 0 since e to the minus x grows much faster than x. So the curve will sort of look like this, and then we'll taper off into words 0. And we're told that we're rotating this solid across the x-axis, so we're doing this sort of rotation. And therefore, when we want to find the volume of this shape, we'll use something like the ring method, where this is like our x, or like our dx. This is our height given by the function, and then we're doing a rotation across the x-axis. So each cross section is defined by a ring. So the area of this cross section is circular, and therefore our area is just going to be pi r squared, where r is determined by f of x at that particular point. So we determine the cross section because we're doing a ring sort of rotation, and so our area of x is simply pi x squared, where x is whatever f of x is at that point. And so our total volume is equal to the integral from 0 to infinity of pi times f of x, which is x times e to the minus x squared dx. So that's the integral we want to evaluate. And because we have something towards infinity, this is going to be an improper integral, and we're going to evaluate it by doing limit as b tends towards infinity of 0 to b of pi times x squared times e to the minus 2x dx. Notice that to find the closed form evaluation of this integral, you'll have to be using integration by parts, but we can save our work by noticing we can use the tabular method to do this. And so through limit, our u will be set to x squared, and then our dv will be set to e to the minus 2x. And so let's continually differentiate. We get that. If we continually integrate, we get negative 1/2 e to the minus 2x. And then over here we get 1 over 4 e to the minus 2x. And then finally we get minus 1/8 e to the minus 2x. This is positive. This is negative. This is positive. And so our final integral will just be the limit as b tends towards infinity of negative x squared divided by 2 times e to the minus 2x, and then this will also be negative, minus x over 2 times e to the minus 2x, and then the last term will also be negative, minus 1 over 4 e to the minus 2x from 0 to b. Therefore, our final evaluation is simply equal to the limit as b tends towards infinity of minus um, minus b squared times e to the minus 2b divided by 2 minus b times e to the minus 2b divided by 2 minus 1 over 4 times e to the minus 2b. And then we'll have a minus sign, and then this term will be 0 since we have x equals 0. This term will also be 0. This is the only non-zero term. E to the 0 is 1, and then so this will just be minus 1/4. And the question just remains to evaluate this under the limit. As b tends towards negative infinity, this will all of the terms with e to the negative 2b will tend towards 0, and they grow at a much faster rate than, like, because this is an exponentially growing term, it grows faster than the power functions that it's attached to. So all of these terms will actually grow. All of these will just go towards 0. So we end up with 0 minus 1/4. And so we end up with 1/4. And I think one thing that I forgot to add when I was doing this work is this pi term that's been passed down. And so the answer is just 1/4 times pi. And so our volume is pi over 4. So hopefully you guys appreciated how this one singular problem had so many concepts that we have been learning about integrals thus far. Not only did it have an improper integral, it dealt with finding the volume through the ring method, and then to even evaluate that integral, we had to use the tabular method, which is a function of the integration by parts. So I think this example was like a really good example to hone in all of your knowledge of integration, and hopefully improper integrals made sense, and you guys are now better with it.